Alright, here are the later examples in 5.2. They're asking us to write this expression in terms of sine and cosine and simplify so that no quotients appear in the final expression. And so what they mean by no quotients is no divisions. They want everything to be good. And just kind of straightforward in one line with no quotients whatsoever. What you'll find is that oftentimes, as I mentioned in the last video, there's more than one way. And so they're trying to teach us some characteristics or some things to look at. So I'll model that, but I'll also model a second way to do the same problem. And so what they're specifically asking us to get practice on is to rewrite in terms of sine and cosine. So what does that mean? We're going to take this guy right here and rewrite it like this. Cotangent, if you remember, is cosine theta over sine theta. Cosine theta over sine theta. And what you have is a complex fraction. And we think back to our algebra days. How do we get rid of the complex fraction? We did it both in Algebra 1 and Algebra 2. We're going to multiply everything through, by the common denominator, which isn't cosine, which is sine. So as I go in here, I'm going to take this guy times sine, this guy times sine, this guy times sine. Every term gets multiplied by sine. Just a nice algebra principle that we're applying here that we've used in the past. What do we have? We have that sine theta plus cosine theta is now sitting over cosine theta. Then we can use the algebra principle that if you have a common denominator like cosine theta, we can split it up. This part right here is very, very useful in calculus. Calculus does not do well with products and quotients. We tend to split things up. So look at this nice split up. Because we have this solid denominator, something that you saw when we were also working with polynomial division. If there was a monomial on the bottom, you would just split it up. We're almost done. Sine theta over cosine theta is tangent theta. Sorry, not equals, plus cosine theta over cosine theta, 1. So that is the way they wanted you to show, to rewrite the 1 plus cotangent theta over cotangent theta into a nice simple statement with no quotients. There was another way, so you can see all this work right here. What if we simply had just done what we did last in the very beginning? 1 over cotangent theta plus cotangent theta over cotangent theta. So they asked us to use this way in which we rewrote in sines and cosines, the way over here. And that's what that looks like. And it all works out. But so does this. You know what you get when you take 1 over cotangent theta. If you have 1 over cotangent theta, if you flip cotangent theta, you get tan theta. And cotangent divided by itself is 1. And so a lot less steps. This is what this work is going to feel like. What matters most is that you're on a path, and each time you're doing something that's algebraically correct. Where you'll get off is if you start to do things that are not algebraically correct. We want you to look at something and make a quick assessment of how to do that, or how to accomplish this. I think it's a really wise advice right here to put everything in terms of sine and cosine as we go down to this part B right here. So let me just take a moment to just rewrite what we have. The first thing's in sines and cosines. So I'm not going to rewrite that, but I am going to rewrite this as 1 over sine theta, and this is 1 over cosine theta. That way you can see how these guys interact. Now what I'm about to write is just FOIL. So I don't have a huge amount of space here. Sine theta times 1 over sine theta is 1. Okay, that's where that 1's coming from. Sine theta times 1 over cosine theta is sine theta over cosine theta. Just simple algebra that we're using. We're pitching the sine theta over 1 times sine theta, that's my top number. 1 times cosine theta is cosine theta, and that's my bottom number. Okay, now we're going to distribute through the negative cosine. So now I'm going to get negative cosine theta over sine theta as I go from here to here. And I am going to get a minus cosine theta times 1 plus cosine theta. Well, that's just a 1. So hopefully those ones make sense to you. Remember, I'll do the last one in case you're thinking that some wicked magic happened there. It wasn't. You have the same thing on the top and the bottom. You end out with 1. If you look closely, our bookends cancel, and so the 1's go away. I'll do that in a different color like red. These go away because there's a positive 1 and a negative 1. You know what sine theta over cosine theta is? It's tangent theta. And cosine theta over sine theta is cotangent theta. Really slick way to go and do that, to use what they suggested. For something like number 82, I would totally recommend that you not put things in terms of sines and cosines and all of that, but that you use the Pythagorean identities. We know that sine squared theta plus cosine squared theta is equal to 1. Now make sure you remember what theta is. Theta is any old angle. So I'm going to take off theta for just a minute. And that means that sines, because this is how you're going to see it in other classes, sine squared x plus cosine squared x is equal to 1. As long as those x's are the same, we're great. Well, if you look here, we have the exact same angle, right? Let me come in there and highlight that. Highlight it in blue. There we go again. Don't know if I'm going to quickly get to where we need to be. We're close right there. Okay. Come back up here. I'm really sorry when that happens. Totally not intentional. But you have, I was going to highlight in blue, you have the exact same angle. So what does that mean? It means, let me come in here with this blue, means that this, you know what that is. According to the Pythagorean identity, it's 1. That whole thing can get replaced with 1. And so what do we have? We have negative secant squared of negative theta plus 1. Now that seems like something. So let me scroll back. I'm going to make this smaller. So as I scroll up, I'm going to come up to our Pythagorean identities. Tangent squared theta plus 1 is secant squared theta. We're going to use that. Let me park that right over here. Tangent squared theta plus 1 is equal to secant squared theta. Alright? Well, what do we have? We have secant squared theta. Well, what about this? It's of negative theta. I don't want to deal with the negative thetas. And in fact, if they're careful, yep, they want it to be on theta only, not on negative theta. So we're going to have to get rid of that. So let's go see what happens with secant in case we forget. Oh, secant's related to cosine, and cosine's an even function. And so it's going to just, secant of negative theta is the same as secant theta. So this is really negative secant squared theta plus 1. So it's a very subtle change there, but I did make a change. This was intentional based upon the fact that it's an even function. This negative sign out here stays. Well, let's make that happen. Let's get that negative secant squared theta. So I'm going to subtract secant squared theta and subtract secant squared theta. I'm going to subtract tangent squared theta and subtract tangent squared theta. And look what I have. I have negative secant squared theta plus 1 is equal to negative tangent squared theta. And guess what this is? Very simply, it's negative tangent squared theta. Perfect. We're done. We have a nice simple form. It has no negative thetas in there. It's reduced down as far as possible. Now, this one is just testing our knowledge. They would like us to evaluate this, and one thing that they're telling us is that cosecant x is equal to negative 3. And they want to know all possible values. Well, I don't think very well in cosecants, so I'm going to change that to sine x then be negative 1/3. So here's what I know from that. I'm either in quadrant 3 or I'm in quadrant 4. That's why they're asking you to give all possible values of that. If we're in quadrant 3, let's think about quadrant 3. All students take calculus. It means my cosine of x value is going to be negative. Let me just write cosine is negative. And right, and so would its flip secant, which is involved. So what do we know? Well, we know that regardless of which situation we're in, and I'll write that up here, sine squared x plus cosine squared x is equal to 1. That means sine squared x, apologize, we know what sine squared x is. I forgot which one we know. That means that negative 1/3 squared plus cosine squared is equal to 1. So you're doing really good math. That means 1/9 plus cosine squared x is equal to 1. That means cosine squared x is equal to 8/9, which means cosine x is either plus or minus root 8 over 9, or simplified plus or minus 2 root 2 over 3, as you know. Well, when's it going to be negative? Right here, the cosine x value is negative 2 root 2 over 3. That means the secant value is also negative. And if I flip that, I'm going to get 3 over 2 root 2, which I know is 3 root 2 over 4. Right? You can hopefully following that okay. The other option is that we're in quadrant 4 and cosine's positive. That was an option over here. So cosine x could have been 2 root 2 over 3, and secant then could have been secant x. Let me not leave it off. Secant x then could have been 3 root 2 over 4. Would have been 3 root 2 over 4. Okay, so that's what we're looking at there. So now we just have to figure out the problem here. So under this scenario, sine was negative 1/3, as it is in both cases, plus negative 2 root 2 over 3, all over negative 3 root 2 over 4. So I'm going to do what I did last time, and that is I'm going to multiply everybody through by the common denominator, which is 12. When I do that, I get a nice negative 4 out, and then minus 8 root 2 all over negative 9 root 2. They'll simplify since everybody's negative, right? Oh no, we got to get rid of the square root. So since everybody's negative, they'll get rid of the negative. I got to rationalize the denominator by multiplying everybody by root 2, so that's negative 4 root. Well, let me get rid of the negative. I said I would do it, and then I didn't do it. Negative 4 root 2 plus, and then this will be 16 all over 18. Multiplying top and bottom by root 2. Root 2 times root 2 is 2, times 8 is 16, root 2 times root 2 is 2, times 9 is 18, and I got rid of the negative because everybody has a negative. They won't leave it like that. They're going to say it's 2 root 3 plus 4 all over 9. And that's one of the answers. Oh, not plus 4, sorry. We're dividing by 2, by 8. So 8, 2 root 3 plus 8 all over 9. So that is one of the possible outcomes. And so they're getting us to really think, right? To just apply this trig in ways, because they know how we're going to be asked to apply it a little bit later on. And so what would it look differently if I was over here? Well, we'd have that negative that we could not get rid of in the top. Everything else would be positive. So we're going to get the exact same thing, except it's going to be negative 2 root 3 plus 8 all over 9. When you plug that in, that's what you're going to get out of that. It's the exact same numbers involved, just alternating signs. So that's it for 5.1. Going through those examples. So I hope that's helpful. They are directly tied to some homework problems, so it's not something that my colleagues and I are making up. It is normal problems that are assigned so that we get practice manipulating things mathematically, which has lots of applications in future classes.